Hi, this is Ashley Broderick, and this is my Lab 4 macroscopic view of DC and RC circuits. As an introduction, the purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional current and potential differences in the circuits, and examine the behavior of ohmic resistors and capacitors. The fundamental principles that were used were energy conservation and more specifically the loop rule, that the change in potential difference is zero for a round trip, current conservation, more specifically the node rule, that the current is constant in time, and that also uses charge conservation and steady state principles, and then series and versus parallel connections. And then in this lab, we'll talk about series and RC circuits and then show that the theoretical and measured values of RC were the same. For this first circuit, the prediction of currents was found using the potential difference divided by the resistance, and the total resistance was found by summing 147 for 147 ohms. And then the current calculations and more specifics are found below each section. And for part 3, the backwards ammeter was negative 0.02 amps, which is just a negative value of the current found in the previous section. For part 4, the ammeter, the current was found to be 0 amps. The circuit is closed, but the voltmeter has high resistance, so the current running is so small the ammeter doesn't read it. Voltmeter, the potential difference was found to be 3 volts. There's no current, so no potential difference for the resistors, only the batteries, which have potential difference of 3 volts, 1.5 volts per battery. The potential differences in closed circuits is shown here. For the potential difference of AB was found to be 3 volts, potential difference of CD was negative 0.959 volts, potential difference of EF was negative 2.041 volts, and the rest were negative 0 volts. Part 6, round trip sum of potential differences, predicted and actual values were 0 volts. For 9, why doesn't the ammeter reading change when attached to the voltmeter? Although the voltmeter alters the current, the resistance is so high, practically no current flows through it, so the change in the ammeter is negligible. The voltmeter across a 100 ohm resistor, the ammeter read 0.02 amps. 11, the ammeter in parallel with a 100 ohm resistor, the current was 0.06 amps. The ammeter decreased the total resistance, resulting in an increase in current. For resistance, part 12, which is the potential difference divided by the current, the values are listed here, and the resistance of the wire and ammeter were 0 ohms. For an RC circuit, the observations were that the battery connected to the bulb and capacitor in series, the light started bright and dimmed as the capacitor charges, and the current decreases as the capacitor charges. The light goes out and the current stops when the capacitor is charged. The capacitor connected directly to the bulb, the light starts bright and dims as the capacitor discharges, and the current decreases as the capacitor discharges. The light goes out and the current stops when the capacitor is discharged. For the time in seconds for the capacitor to charge and discharge, for the 10 ohm bulb, it was approximately 10 seconds to charge, 10 seconds to discharge. For the 20 ohm bulb, the charge took about 20 seconds and the discharge about 20 seconds as well. This is my time-dependent voltage across the discharging capacitor for RC circuits, and here the slope was found to be negative 0.1667, and the slope is also negative 1 divided by RC. So RC was found to be approximately 6 seconds, which is the same as the predicted RC value of 6 seconds. For the first question, if we were doing this lab in real life and used an actual ammeter, what would be different and how would it have affected the circuits? So a real ammeter has resistance, unlike the virtual ammeter, which would be perfect and have no resistance. This causes there to be a potential difference from one end of the ammeter to the other, affecting both the overall potential difference in the circuit and the current. For question 2, if you were doing this lab in real life and you use a real battery to charge the capacitor with no resistor, how quickly would the ideal model predict the capacitor to reach full charge, and would this prediction happen in real life? So with no resistor, the capacitor would charge much more quickly than with a resistor present in the circuit. So in the ideal model, it would predict the capacitor to reach full charge the second it's attached to the battery, but this wouldn't happen in real life since the model assumes negligible electric field and resistance in the wires and battery. In real life, there is a small resistance in batteries and wires, slowing down the charging of the capacitor compared to the ideal model. So in conclusion, our RC values were found to be approximately the same, and this gives us a good overview of series in RC circuits. Thank you.